Okay, so I listed out the steps that we're going to be using to actually collect data from the gyroscope. So again, the first thing we want to take into consideration is that we want to set the SPI mode to 3. And after that, what we want to do is double check if we're actually communicating with the gyroscope correctly. So part A is testing we're connected with the gyroscope. So we're going to be reading the Who Am I register, or the ID register of this gyroscope. The address code is going to be 143. This includes the read option for it. And then we're going to check if the gyroscope responds. And if it outputs 212, that means we are connecting with the gyroscope and we can actually talk with the gyroscope. Since we had that done and over with, we're going to go ahead and initialize the gyroscope. So that means we're going to write to the first gyroscope control register, which has an address code of 32 to 15. By setting to 15, what that means is we're going to set the sampling rate to 95 samples per second. We're going to enable all the axes to be read. So we can actually collect data on the rotations around the x-axis, the y-axis, and the z-axis. And that on top of all that, that also turns on the gyroscope, so we can actually start collecting data with it. Then we're going to write to the fourth gyroscope control register. The address code is 35, and then we're going to set that register to 16. By setting it to 16, what we're going to be pretty much doing is we're going to be setting the sensitivity range, or the full scale range, to plus minus 500 degrees per second. Okay. So the next thing is, after that, once we have it all set up and it's all initialized, then we can collect data from the gyroscope. So that means we can actually read 2 bytes of the angular velocity data around the x-axis. So that means the address code for that is 232, and you're reading 2 bytes of data. Then you're going to do that for the y-axis, and the address code for that is 234. They're going to read around the z-axis, and that's going to be 236. And then we're going to pretty much, once we get to collect this data, we can probably print it to the computer, and we can actually see that output.
Okay, so what I have here is the LSM9DS0. It's actually at the very center right here, so this is the actual chip itself. But again, I bought this from Adafruit Industries, and it's pretty much a breakout version of it. So it makes it so that all these little small pins right here are actually connected to these pins right here. So we can put this on a breadboard. And with that as well, there's also the few pins that you might need to know. So there's actually ones on the top right here, but these aren't necessary. These are for interrupts if you want to use them, but we're not going to be using them. Alright, so the bottom right here is 3.3 volts, ground, and again, this has an I2C interface, so you're going to see a serial clock and SDA as the I2C pins. But for the case of SPI, the serial clock pin for the I2C is the same thing as the clock pin for the SPI. SDA for us is master out, slave in, or it's considered the data line in this case. CSG is the chip select for the gyroscope. CSXM is the chip select for the accelerometer and the magnetometer. SDOG is pretty much the master in, slave out for the gyroscope, and the SDOXM is the master in, slave out for the accelerometer and the magnetometer. So we're going to go ahead and wire this up. We put this down on the breadboard. Now we need to connect this to 3.3 volts. I'm going to go ahead and find 3.3 volts here. And we see 4 pins down. 1, 2, 3, 4. And then connect this to 3.3 volts. And then we are going to go ahead and find the ground pin on this. Connect that to ground. Okay, once we have that all set up, now we need to go ahead and select the SPI pins that we want to use. So we can use PTC, we're going to be using PTC6, PTC7, and PTC5. PTC5 is for the clock, so let's go ahead and locate PTC5 here. So PTC5 in this case is right over here. So it's the middle pin. So it's pins 1, 2, 3, 4 down from there. So 1, 2, 3, 4 right here. Right, it's going to be connecting to our clock. So it's going to be connected to SCL, this chip. Then we need to connect SC, PTC6 and PTC7. So we find PTC7. So PTC7 is on the bottom right here. And for the sake of this, we're going to go ahead and connect this to the gyroscope. What's it called? The gyroscope output. So SDOG. Then we're going to go ahead and connect up, find PTC7. Well, actually found PTC7 last time, so it's going to PTC6. And PTC6 is right above PTC5. And this is going to be for our master out, slave in. So this one is be connected to SDA. Now we need a chip select pin for the gyroscope for the first part of this. So let's arbitrarily select one pin that's convenient for us. I would say we'll use PTC0. So we're going to use PTC0, which is right over here. And this is going to be connected to the chip select for the gyroscope. Alright, so that's it for the first part. We're just going to be connecting this up to the gyroscope. And the next part, we're going to go ahead and add the few parts you needed to connect to the accelerometer and the magnetometer. Okay, so let's go ahead and get started. So what I did was I just went ahead and created a file that we're going to be using to write the code. I already imported the mBed library, so we have all that set up. Okay, so with that I also did add the comments. So what I did is I commented out exactly which pins we're using for SPI, and also just the comments of exactly what our code should be doing. So let's go ahead and get started. All right, so the first part is we want to actually initiate SPI, so that means we're going to type in capital SPI. And what do we want to call this class? So I'm just going to say lowercase SPI. And then the input arguments are the master out slave in pin, the master in slave out pin, and the serial clock pin. So I'm going to just type in PTC6, and then PTC7, and then PTC5. Okay. And then we want to create a chip select pin for the gyroscope. So that's any sort of arbitrarily digital pin that turns on and off. So I'm going to say digital out. Gyro, CS pin, and this pin is PTC0. Okay, go ahead and type in int main. So that's the main function that's going to be running at this main code right here. Okay, so we want to set the SPI mode to 3, so that means we're going to type SPI.format 8 bits, which is the 8-bit transfers, which is typical, comma, the SPI mode, which is 3. And then we're going to set the frequency, just for the sake of it, SPI.frequency. Again, the fastest clock speed you can have with this chip is 10 megahertz. We're going to go ahead and set it to 8 megahertz. So 8 million, so that's 8, 1, 2, 3, 1, 2, 3. That's what mega means. Okay. Next part is we're going to go ahead and test to see if we're connected with the gyroscope, and we're going to go read the who am I register and see if it outputs 212. So let's go ahead and do that. So first off, you want to set the gyro chip select pin to 0, because by setting it to 0, that means you're actually going to start communicating with this the gyroscope on this chip. So we're going to go ahead and say SPI.write, and we're going to throw in the address code for that, it's 143. And then right after that, immediately after that, it should respond to it. So we're going to go ahead and read that. So we're going to say just int who am I value is equal to SPI.write, and anything you want to put in here. Typically, you throw 0 if you just want to just read something. So again, you're gonna write 143. It's gonna respond back, and it's gonna be stored. Whatever it outputs is gonna get stored to who am I value. So then we're gonna go ahead and figure out if what we got is actually 212. So I'm gonna make an if statement here. Let's say if who am I value equals 212. Then we're going to go ahead and do something with that. So I think in this case, I'm just going to go ahead and print to screen gyroscope is working /n as meaning new line. So if you cover the serial communications tutorial, you'll realize that this should actually be pc.printf. But in the case with mBed, by typing in printf, by default, that means you're interfacing with the USB that's connected to the computer, and it's going to be set to 9600 baud. So it's just a faster way of creating serial communication. So instead of saying serial, PC, and then USB transmit, and the USB receive, you can just type in printf. So with that, if it responds, if it actually gets near 12, it's going to respond by saying gyroscope is working. Else, I'm going to just create an else statement just to make sure that it actually did output something. I'm going to go say that gyroscope is not working. So I'm going to say printf gyroscope is not working. And I'm going to say /n as meaning new line. Okay, so that should be it. I'm going to go ahead and test this out. And I'm going to go ahead and compile this. Okay, so I went ahead and uploaded the code, and I have CoolTerm set up, and I'm
right now interfacing with the microcontroller. So I'm going to go ahead and see if it's actually working. So let me go ahead and just hit it. And apparently it's not working, huh? Alright, so I seem to have found the problem. So apparently SPI mode is not actually 3, it actually works best at 0. I don't know exactly why that's the case, but we're just going to go ahead and work with that, even though the spec sheet says SPI mode 3. I went ahead and just added this over here. So it's always a good idea that after when you do a write command and transfer and read data, it's a good idea to pull it back up high just to end the SPI communication. So I just did that right there. Alright, so we're going to go ahead now and do the next step, which is to initialize the gyroscope. And it says write the first gyroscope control register address code 32 to 15. So I'm going to go ahead and do that. So we're going to just first pull the chip select pin down low again, just to initiate the communication line. And then we're going to give it like, I would say 3 microseconds. So this is wait underscore microseconds. So we're going to wait 3 microseconds before we do the next thing, just so that everything settles down. And then we're going to go and do SPI.write 32. And then we're going to do SPI.write 15. So that pretty much means we're going to transfer 32 and then we're going to transfer 15. So 32 is just the control register value, and this is the one that we're actually going to actually change it to. And we're going to go ahead and just wait a couple of microseconds again. So wait 3 microseconds before we do the next thing, and then we're just going to go ahead and pull this up high just to end the SPI communications. Equals 1. Okay. All right, the next part is pretty much the same thing because it's a write. So we're going to go ahead and write to that. So I'm going to go ahead and just copy paste this because it's pretty much the same thing. All I just have to do is make a few changes. So all I have to do is change, instead of writing to 32, I'm going to write 35. And instead of writing 15, I'll write 16. So that should do it for both of the initialization steps. Now we're going to go ahead and just read data from the gyroscope. So I'm going to go ahead and start the communication by pulling the chip select pin low. Then I'm just going to wait 3 microseconds for everything to settle down. And then I'm going to do SPI.write 232. And then now we're going to read in 2 bytes. So what I want to do is I want to use a short. Short is a integer type that stores 16 bits. There's a reason for this, which I'll explain later. But we're going to be reading in 2 bytes. So I'm going to say this is the gyro x-axis low bytes is equal to SPI.write. Again, the SPI.write command is also used to read things in. So I'm just going to set that to 0. And I'm going to go ahead and now read the next byte. So gyro x-axis high byte is equal to SPI.write 0. Okay, with that, we're going to go ahead and just bunch these two bytes together and turn it to a 16-bit number. So I'm going to say short gyro x-axis is equal to gyro x-axis high byte, and we're going to shift this up by 8. And then we're also going to stack the gyro x-axis low bytes on top of this. Alright, so let me just go ahead and explain exactly what I did here. So these are bit shift commands. So the idea is that, let me just say that I have an 8-bit number. So I'm going to just fill the bottom up with just net ones. And I'm going to go ahead, the idea is I want to move this all the way up to here because these are technically high bytes. So I'm going to go ahead and shift up 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then I'm going to go ahead and use the OR command. So the idea of the OR command is that whenever it sees a 0 and a 1, it'll become a 1, and whenever there's 2 1s, it'll become a 1, and when there are 2 zeros, it'll become a 0. So I hit OR, and then if I say use the number 255, which will have all of these as 1s, if I go ahead and press equals, you'll actually see that they all stack up together like that. So that's what we're pretty much doing with this case. Okay, so once that's done, we're going to go ahead and just wait 3 microseconds again and pull the gyro chip select pin high again. Okay, so that's how you pretty much read in the case for this sensor. So I'm just going to go ahead and just copy paste this because it's pretty much the same thing. All I just do is I just change the register and just the name of the variables. Okay, so this is now 234. I'm going to say this is the y-axis. Okay, that does it. I'm going to go ahead and copy paste again. And you can see it's 236 this time around, and this is for the z-axis, so I'm going to just go change this to z. Z-axis high and z-axis low. Alright, and that pretty much does it. So all we have to do now is just print this to the screen so we can actually see the data. So I'm going to say printf gyro x %d. This is just a placeholder just to store the integer value of the x-axis data. Y %d. This is just to store the integer value of the y-axis data. Z %d. This is just to store the integer value of the z-axis data. It's a placeholder for it. And then you just type in gyro x-axis, gyro y-axis, and gyro z-axis. So what it'll pretty much do is it'll just get those values, these values, and it'll just throw them into here. So the %d is what these numbers are going to be. So it's going to get this number and it's going to just stick it right here. And on top of all this, I want to just make it a new line. And this entire thing, because it's in a main loop, it's going to do it only once. So I want to actually put all the read operations in a while loop, so that it just keeps reading continuously. So I'm going to say while true, and then end the while loop at the end of here. And on top of that, I just want to make it wait, 0.5 seconds before it prints again, just to ensure that like the serial monitor doesn't like throw up around a series of numbers that we just can't really see. So that's pretty much it. I'm going to go ahead and compile this and throw this into the microcontroller, and we'll see what it outputs on the screen. Okay, so I just uploaded the code. I'm going to go ahead and connect to the microcontroller, and we're going to actually read out what the gyroscope is saying. So I'm going to go ahead and do that. Okay, so it's actually outputting numbers, and these are very low numbers. For some odd reason, it actually outputs a very high value at the z-axis. That's particularly one issue with these sensors, is that they need to be calibrated beforehand. And like when these are actually being soldered onto the board, they actually might fluctuate a little bit here and there. So a good idea that we could do in this code is just let it settle down for the first 5 seconds, read the average value here, and set that equal to 0. But we're not going to go ahead and do that because we have to cover the accelerometer and the magnetometer. But let's go ahead and have a little bit of fun with this. So if I rotate around the z-axis in one direction, it actually is it's negative, and the other one direction, I rotate the other way, it's actually positive. Oh, it's actually the other way around. So this way is positive, and this way is negative. And then if I rotated this in the x-axis, you see that this is a negative, and this is a positive value. Negative, and this is positive. All right, and the z-axis is this way around, so if I move it up like this, you can actually see the change in the y-axis values. So let me go ahead and just settle this down. And if I move this in this way, this is positive. I move it this way, this is negative. So this is positive, and then this is negative. So pretty fun. Let's go ahead now and attach the accelerometer onto this and the magnetometer to have a look, and just go ahead and read those data values out.